Welcome to the lecture. You may kindly recall that in the earlier lecture we had discussed the basic concepts of the forecasting, and we had understood the concepts of within sample forecasting, outside sample forecasting, actual value prediction and average value prediction. Now, using the framework of multiple linear regression model, we are going to construct the predictors, and we are going to understand how to find out the statistical properties of these predictors. Based on that, we can judge whether our forecasting is going to be good or bad. So, firstly let us try to consider the within sample prediction or within sample forecasting. Right. So, let us try to first establish our framework. So, we are going to use here the model y is equal to x beta plus epsilon, where y is a n cross 1 vector of n observation on the response variable or steady variable, x is a n cross k matrix of k explanatory variable, where each explanatory variable is having n observation. Beta is a k cross 1 vector of regression coefficient associated with x1, x2, xk, and epsilon is a n cross 1 vector of the random error component, and we assume that epsilon is following a normal distribution with mean vector 0 and covariance matrix sigma square I. And we already have seen that this beta is unknown, and we estimate beta by beta hat as say x transpose x whole inverse x transpose y. Now, based on that, we try to construct a predictor, and this predictor is constructed like p is equal to x beta hat. Okay. Now, suppose we want to forecast the value of y at x equal to x naught, which is a given point. Then forecast is going to be p hat is equal to x naught beta hat. Right. So, for example, if I say that we are given, suppose the first value of x1 as say x1 naught, second value of x2 as x2 naught, and so on, the kth variable is having the value xk naught, then your predictor is going to be beta 1 hat x1 naught plus beta 2 hat x2 naught up to here beta hat k xk naught. So, now this is our predictor, which is based on the ordinary least square estimation or equivalently the maximum likelihood estimation, and now we will try to use this predictor to forecast the average value and the actual value. So, first of all, we consider the forecasting of average value, expected value of y. Okay. So, in this case we are going to use the predictor as say p is equal to x beta hat. Right. So, now I would like to know the statistical properties and performance of this predictor when it is used for forecasting an average value. Okay. So, in the first step we try to find out the prediction error, or this is called forecasting error. You see, if we are using here the terminology prediction and forecasting exactly on the same line, there is some minor difference between the two, but we are not going into that detail. Okay. So, this prediction error is given by p minus expected value of y. And if you try to see, this is based on the same concept as in the case of an estimation error. For example, when we are trying to estimate a parameter theta by theta hat, then we try to find out the estimation error as theta hat minus theta. Okay. So, similarly here also we are trying to know the value of expected value of y using p. So, if we try to simplify it, this is nothing but x beta hat minus x beta, and which is x beta hat minus beta, and this is nothing but your x transpose x whole inverse x transpose epsilon, and this is nothing, this is in our symbolic notation, this is h epsilon, where h is our hat matrix given by x transpose x inverse x transpose. Now, based on that, we try to first see whether this is an unbiased predictor or not. So, we try to take its expectation and expectation of p minus expected value of y, and this comes out to be h expected value of epsilon, which we have assumed to be 0. So, this is a null vector. So, this implies that p provides unbiased prediction of average value. Okay. Now, next we try to find out the predictive variance. And this is defined as say PV, and I am writing here M means mean value. Okay. So, the predictive variance for P forecasting the mean value, this is given by expected value of P minus expected value of Y transpose P minus expected value of Y. Okay. So, this value we already have found, this is expected value of epsilon transpose H into H epsilon, which is expected value of H is an idempotent matrix. So, this is S epsilon transpose H epsilon, and this quantity is nothing but sigma square trace of H, and trace of H is nothing but K, sigma square times K, right. So, this is our predictive variance when P is used for predicting the average value. Now, we observe that this predictive variance depends on sigma square that is usually unknown in practice. So, an estimate of predictive variance can be obtained by replace sigma square by sigma square hat, and the sigma square hat is obtained from the analysis of variance as sum of square due to residual divided by degrees of freedom, and this is obtained from analysis of variance. So, in this case we can write down that the predictive variance has an estimate as sigma hat square times K. Okay. So, now we have described here a predictor, we have obtained its prediction error, and we have shown that it will provide us unbiased prediction, and its predictive variance is given by sigma square K, and this can be estimated on the basis of given sample of data using sigma hat square K, right. Now, in case if you want to have the prediction interval, then the prediction interval can be obtained as follows. We will have here two cases when sigma square is known. Then in this case we know that P minus expected value of Y divided by standard error of P, this follows a normal 0 1. Okay. So, now based on that we can write down here probability that minus z alpha by 2 P minus expected value of Y and standard error lies between z alpha by 2 is equal to 1 minus alpha, where z alpha by 2 are the values which are obtained from the normal tables, as we have done in the case of regression parameters also. And so, the 101 minus alpha % confidence interval for expected value of y can be obtained by solving this inequality, and this gives us p minus z alpha by 2 square root of PVMP and p plus z alpha by 2 square root of PV predictive variance of p for mean values. Okay. Now, there is second case. Second case is that when sigma square is unknown. In this case, we know that predictor minus expected value of y divided by the standard error of p. This follows a t distribution with n minus k degrees of freedom, and in this case the critical value are minus t alpha by 2 n minus k less than equal to p minus expected value of y over square root of estimate of predictive variance for mean t alpha by 2 n minus k degrees of freedom is equal to 1 minus alpha, and based on that 1 minus alpha % confidence interval for expected value y is obtained as p minus t alpha by 2 n minus k standard error of p and p plus t alpha by 2 n minus k and standard error of PV. So, this is the confidence interval for expected value of y when sigma square is known and when sigma square is unknown. The next aspect, we try to consider it for actual value prediction or actual value forecasting. So, we are interested in forecasting the value of y. Okay. So, now we are going to use here the same predictor. So, same predictor is being used for average value forecasting and as well as this is being used for the actual value forecasting. So, this is actually called as dual nature of predictor. Well, that is happening because we are using the ordinary least square estimator in both the cases, and in practice one may use different estimators to forecast the average value or actual value. One question arises here that when we are trying to use the same predictor for forecasting the actual and average values, definitely it will give us the same value. Then what will be the difference? So, the difference will be seen by comparing the standard errors. Okay. So, let us try to investigate the properties of this predictor when it is used for actual value forecasting. So, first of all, we try to find out its prediction error. So, since p is being used to estimate or to know the value of y, so the estimation error is given by p minus y, and p is our x beta hat and y is our x beta plus epsilon. So, this can be written as beta hat minus beta minus epsilon, and this is minus times I minus x transpose x whole inverse x transpose epsilon, and this is minus h bar epsilon, where h bar is nothing but I minus h, and h is x transpose x whole inverse x transpose hat matrix. Right. So, now from here we observe that expected value of p minus y, this comes out to be null vector. So, this implies that p provides unbiased predictions when used for actual value forecasting. Okay. And next we try to find out the predictive variance. So, predictive variance in this case, let us try to write down here as say A. A means actual. So, this will be expected value of P minus Y transpose P minus Y, and this is nothing but your expected value of epsilon transpose H bar into H bar epsilon, and this is nothing but expected value epsilon H bar epsilon, because H bar is an idempotent matrix, and this quantity is nothing but sigma square trace of H bar, which is sigma square n minus k. Okay. Now again the question arises that this sigma square is unknown. So, we can obtain here an estimate of predictive variance. So, this can be obtained by just replace sigma square by sigma square hat, and that is obtained from the analysis of variance as sum of square due to residual divided by the quantity n minus k, right. So, in this case an estimate of predictive variance of P when it is used for actual value turns out to be sigma hat square times n minus k, right. Next, we try to obtain the prediction interval. In this case can also be obtained exactly as in the case of average value forecasting, and we will have here two cases. When sigma square is known, then in this case the prediction or forecasting interval turns out to be P minus Z alpha by 2 P predictive variance of P for actual value, and P plus Z alpha by 2 standard deviation of P when it is used for actual value, and the second case will be when sigma square is unknown. And in this case this prediction interval is T distribution with n minus k degrees of freedom, and this will be standard error of P when it is used for actual value, and P plus T alpha by 2 n minus k, standard error of PV of P when it is used for actual value prediction. Now, another interesting question comes here, that we are using this P for making a forecast for average value as well as for the actual value. So, in case if we try to compare it, that P is, then we can say that P is better for predicting expected value of Y than predicting the actual value Y when the predictive variance of P when it is used for forecasting mean value is smaller than the predictive variance of P when it is used for actual value, and this gives us or k less than n minus k, or I can say this n is greater than 2k. So, that means this is the total number of observation should be greater than twice the number of explanatory variables. So, that is a very simple condition under which we can know that that the same predictor is going to perform how under which type of condition. Right. Okay. So, we stop here, and in the next lecture we will try to concentrate on the outside sample prediction under a similar setup, and we will try to take one example where we would like to see how does these values comes out and how do we take an inference on them. Till then, goodbye.